All right, who here likes Java? Yeah, me neither. Necessary evil. So I'm here today to talk about garbage collectors in Java. There's this thing called G1, the garbage first collector. It's the new default. Most of us are familiar, if we're familiar at all, with concurrent mark and sweep. And especially for real-time services, G1 collectors is a little scary. It is a pure stop-the-world collector. There is no way to go through a collection cycle without pausing the application for some amount of time. So we'll talk about how we can make this work for real-time services. So when we think about scaling, we have to think about what trade-offs we're willing to make. Scaling doesn't mean writing Jeff Bezos and Amazon Web Services a blank check. That's the opposite. That's throwing hardware at a problem. Scaling means understanding what trade-offs you're willing to make, someone want to shut that door maybe? Understanding what trade-offs you want to make, like space versus time, the classic computer science dilemma, which we can think of in the context of the G1 collector as the amount of usable heap that we have, modulo our CPU speed and our cores. So this implies that you have the capability to measure your service, that you have the capability to measure the things you care about, so that you're able to run experiments, evaluate how tuning different knobs affects your workload, affects your user experience, and be able to iterate. If you can't do those things, you're stabbing in the dark. It means you should go back to the drawing board, develop the capabilities to measure your service effectively, and then focus on tuning. You should also think about what your load profile looks like. Your load profile is, your service over time. We are not running constant traffic on Messenger. With Messenger, we've got peak. It starts at about 4 a.m. on Pacific Standard Time, runs until about 10 a.m. Pacific Standard Time. After that, we experience a lull. And understanding how our service ebbs and flows, the number of requests we get, the amount of object creation that we have, the amount of new users connecting, that really informs our ability to make choices around like how we want to perform during peak and how we can use the extra time, the extra cores, the extra heap that we get post-peak to clean up after ourselves. You should also think about like what's the minimum your tax needs? What is a tax? At Facebook, we like to call this the FB tax. It's all the things running on a server we can't control. On top of the page cache, because we're running on Linux, most of you are probably running on Linux or something similar, we've got things like OS Query. We've got Chef running on every interval. We have a series of stats collectors, other daemons, agents, things like that, that get to use our processors, get to use our core, get access to memory, and we need to take these things into account. We're not going to get to use all of the heap on the machine. We're not going to get to use all of the cores on the machine, so we have to be accommodating, because under the worst case, we're still going to need to be performant even when those other tasks aren't behaving well. So G1 is kind of the future of yesterday today. It's been around for a while. It's been around since about 2006, 2007, and it was experimental. It was developed in academia, and over the last several years, it's been hardened, gone through several iterations to improve performance, fight corner cases, and now G1 is ready for production. At Facebook, we're running G1 in production for all of our MQTT servers throughout the world, globally in production. This change materialized around March of this year. So we're going to start with, if we think of computers as we have data and then algorithms that act on them, we're going to start by talking about the heap and its layout, and then the cycle of a GC life cycle. So the first part of the G1 is we have Eden space. This is kind of what it sounds like. We have Eden is where all new objects get allocated. After that, we've got survivor space. Survivor space is where we copy out objects that survive a collection cycle contiguously and then promote those regions into either Eden space or tenured space, depending on our tenuring threshold. If we ever run out of survivor space, we will do a full GC. A full GC is where we stop the application entirely, clean up all possible garbage, and then resume. If you have a latency-sensitive service or a real-time service, this is the worst possible thing that can happen. So we must design and tune our collector profile such that we never encounter a full GC. If in your testing you ever encounter a full GC, then you have to go back to the drawing board. It's not going to work. Full GCs are never going to be acceptable unless you specifically, at the front end of your application, identify machines that are going to go into a full GC cycle, take them out of production, redirect traffic away from them, and invoke the GC yourself. Then we have tenured space. Tenured space is kind of like tenured in academia. It's been around for a while. We're going to worry about it later. We do less bookkeeping on tenured regions. And the trade-off is we do less bookkeeping, we spend fewer CPU cycles on it, with the assumption that if it's been around for 7 or 8 or 9 or 15 collection cycles, it'll probably be around for what might look like forever. After that, we have free space. Just enough, not too much, not too little, just right. You want free space to be in a Goldilocks zone. So let's talk about the structure of a region. A region is divided up into the objects that compose it, as well as the metadata that informs us about those objects. A region can be between 1 megabyte and 32 megabytes of space on your heap. We've got some number of objects that are alive, some number of objects that are garbage. And we've got our remembered set. Our remembered set is the bookkeeping, the metadata that tells us which objects are alive and dead. And that lets us express for that region a liveness percent. And each region's liveness percent gets updated every young garbage collection cycle, which then helps us tell the garbage collector what choices to make when it performs evacuation and cleanup. And the collector strives to be as efficient as possible, and so by giving it the right information, it can make the best choices possible. So G1 has a collection life cycle. Now, I'm going to kind of breeze over the details. The important thing is that some phases stop the world, some phases update the remembered set and the other metadata, and some phases work concurrently. That's really all you need to know. This is kind of a roadmap for like the broad overview of how a lifecycle works, so that if you decide you want to go and try out, tune, get G1 working or working better for your application, you have the right context on where to start. So at the very beginning of a collection, we have what's called a marking cycle. Now this is a stop the world cycle. Now, the reason that we stop the world here is because doing this concurrently is really inefficient. It's one of the things that we found with Concurrent Mark and Sweep and other highly concurrent garbage collectors, is that things change out from under us. If we look at something, we look over here, oh, this changed. Now we've spent additional CPU cycles keeping track of things as they change, and that's really inefficient. So by stopping the world, we can go and decide, hey, these objects are alive, these objects are garbage. Then we resume and move into root region scanning and marking, which is concurrent. What this allows us to do is track objects and the references to one another across different regions, and then we'll halt again, stopping the world, and finish up our marking work. And it's here in remark where we update the remembered set liveness. And it's important that this is kept up to date because it can become stale. This remembered set update only happens during a young GC cycle. And so when we're pruning tenured in mixed collection cycles, where we prune both young and tenured regions, we can actually have this liveness percent become stale, and then the collector is not going to be making intelligent choices on which regions to evacuate and copy out first. Because when we move to cleanup, right, like the first thing to do is like regions that are entirely dead, that's the easy thing to do. That's the no-op. We can give that memory back to the application right away, so we do that first. Then after that, we have our collection set. A collection set is the set of regions during a given collection cycle that the collector will first evacuate and then free up. So there are two kinds of evacuation. The important part is that in both, we copy live objects out from regions in the collection set into new memory in the survivor space and then free the old ones. Now, the important part is that only in one of these do we update the remembered set liveness percent. That's in the young GC collection cycle. In the mixed GC collection cycle, that's the only time we're ever going to evacuate and clean up tenured objects. That begs the question, what does tenured really mean? Tenured means it's lived for a while, it's probably going to continue for a while. Now, as you can imagine, long-lived doesn't necessarily imply forever. What is long when it comes to computers? Is it 5 minutes? Is it 10 minutes? The average lifetime of a connection to Messenger is about 15 minutes. So you open up Messenger on your phone, it spins orange, says connecting, then it turns green, connected. You'll probably live for about 15 minutes, then you'll run, hop on the train, you'll hop off of your home's Wi-Fi maybe, onto LTE, you'll get to your work, you'll hop on your work's Wi-Fi. Now you've cycled out 3 times, and we have to clean up those objects. But if your train ride was like 12 minutes, for computers, that's like forever. And so for us, though, that seems kind of young. And young versus tenured, like Eden space versus tenured space, dies instantly versus lives forever, these are kind of false dichotomies. And so we have this implicit assumption in G1 about liveness, which is that we have long-lived and short-lived, and that's it. But for Messenger, in particular, like, lives for 15 minutes does not mean lives forever. For us, we really decided we thought more of this as medium-lived. We have short-lived objects, medium-lived objects, long-lived objects. So how do we take a dichotomy and move it into a trichotomy? Well, it doesn't work well for us. And when we first deployed our first experiments running G1 in the JVM, we ran into this problem, where we would have our tenured heap space growing monotonically until we ran out of heap space entirely. We exhausted survivor space. We encountered a full GC, stopped the world, 30 seconds to several minutes, clean up all garbage, resume. Yeah. For a real-time service, that doesn't work. And this is a non-starter. And so we had to think about, what do we need to do to make this work? Well, for MQTT, the Messenger Network Edge Transport Service, we have some number of connected phones, Messenger.com instances, Instagram direct messenger instances, and those are long, but then they'll die off. But I thought, what should our graph look like? What should our tenured occupation graph look like? And it should look like, it should bend toward and curve toward the number of users that are actively connected to a given instance at any given time. This implies that we need a capability to prune objects from the tenured heap as fast as they die. And with mixed GCs, we only even start looking at cleaning up the tenured heap after the default occupation threshold. What is the default occupation threshold? It's 65%. So if you're only using 50% of the usable heap, G1 will never purge a tenured object. The next problematic default assumption that we encountered is that in the collection set, during a mixed GC, only 10% will be tenured regions. So even if you've got a lot of garbage in your tenured heap, by default, 90% of your cleanup operations will be focused on the Eden space, on the young generation. And this doesn't work well either. We bump that up to 50%. The next problem is, remember that liveness percent? Well, by default, a region must be 65% alive or less to be even considered for the collection set. So you can imagine a world in which we have used, or of our tenured space, we've got maybe 20% dead objects, 20% garbage, spread out evenly across our tenured regions. We will never, ever include a tenured region into the collection set. And the result is that you get very fragmented object death across your heap, resulting in a monotonic growth in your heap usage followed by full GCs. So this implies that the default ergonomics of G1 GC don't work for real-time applications. They don't work if you have objects that live for quite a while and then die. Because most objects for real-time services like ours do not live forever. And neither does the battery. All right, so I'm just going to use the microphone then. So I'm going to go through a few different options that you can set. In some cases, there are walls of text. This is really there for those who want to pull the slides later for tuning themselves. If it looks like there's a lot of text, ignore it, focus on me, and I'll try and just summarize basically the options and what they affect. The G1 old CSET region threshold percent, basically that is, the default is 10%. That is what we can include into our collection set during a mixed GC of tenured regions. We bumped this up to 50% so that every mixed GC lifecycle, we were including up to half of the regions would be tenured. So this meant we were able to evacuate tenured space more frequently and bend our curve of tenured occupation toward the number of live endpoints attached to our service at any given time. We also wanted to make sure that we were constantly pruning the tenured heap. We want to begin, force G1 to begin mixed GCs immediately. By default, this is 65%. We changed it to 0. Then after that, we found out that G1 liked to change it back, because there's this thing called adaptive initiating heap occupancy. Some parts of the G1 adaptability worked well for us. This was not one of them. We want to continuously purge the tenured heap, so we turned off adaptability, set the default, or set the percentage for initiating heap occupancy percent to 0, and then we changed the G1 mixed GC live threshold percent. This is of the collection set, or sorry, to be included in the collection set, how alive can it be? The default is 65%. We changed this to 90. So that may be less efficient, but what it resulted in is that after peak, we would scrub with the extra CPU cycles we had the tenured heap and keep objects pruned pretty well. So we actually would rely on the ebb and flow of peak and post-peak and leverage G1's adaptability in order to keep our tenured heap pruned pretty effectively. We also reduced the mixed GC count target from the default is 8, but because we were doing it constantly, we reduced it to 4. We would do a young GC, then 4 mixed GCs, then a young GC and 4 mixed GCs. This is important because it's only during a young GC that the remembered set liveness is updated again. And if we use the default, we found that it would become too stale. The collector would make poor choices. After that, we've got the max GC pause millis. Now, this is just a hint. It should be a realistic hint. Because remember, real-time services are not actually real-time. None of us are using quantum entangled qubits to push data, right? We're bounded by the speed of light, and while it seems pretty fast, in general, it's actually, we know it's pretty slow. So when we say real-time, what we're just saying is we're bounding the latency with something we find tolerable, and we're ruthlessly staying within those constraints. So you should make a realistic assessment of the latency that you're willing to tolerate, put it here, and then go and measure, measure, measure. Once you do that, you can find that G1 actually doesn't just work passively. We found that G1, properly tuned, allowed us to reduce our server footprint by over 10%, as well as we saw 10x improvements in latency reduction at the P99, P95, and P90 bands. G1 is both faster, lower latency, and more efficient than concurrent Mark and Sweep and properly tuned. I'm Andy Chalfant, production engineer at Facebook on messaging infrastructure. Anyone have any questions?
So you mentioned that you tuned your tenured mixed GC threshold to 90%, and then you changed up your number of live objects in the tenured heap to be collected each time mixed GC to 50%. Doesn't that increase the amount of time per GC?
No, so the amount of time per GC is bounded basically by the hint that you make. So if you say hey, don't pause for more than 500 milliseconds, it takes the liveness percent that it ranks eligible regions for inclusion in the collection set. And then evaluates how long it thinks evacuating all those objects and then freeing up the region will take. And then it tries to do its best in that amount of time.
But how do you arrive at that 400 millisecond number?
What I actually did was I drew a graph. I ran several different experiments, and then ran a graph basically on like invocations versus pause time to try and find like, what you find is that it, like, let's say you reduce it to like 50 milliseconds. What you find is that it invokes itself far more frequently and has very little throughput. Yeah. And so you want to find the inflection point between infrequency of invocation with throughput for evacuation. And if you draw that over a graph and you do like 100 milliseconds, 200, 300, 400, up to like 1,000 milliseconds, find out where the inflection point curves down to, and what trade-offs you're willing to make on like how real-time or like how latency responsive your service feels.
Good. Thank you.
Hi, thanks for the talk. I'm assuming before you switched to G1, you used something like Concurrent Mark and Sweep.
Yes, we use Concurrent Mark and Sweep.
So I'd be interested in the strategy of how did you canary that new change? Like how long did it take you? How much traffic did you use to canary it? How long did you do these observations for? What did you learn, and what would you have done differently?
I learned first that just because something works effectively for an hour to 2 hours doesn't mean it's going to work for 48 hours. You have to run long canaries, because we declared success prematurely on several occasions because it worked great for 3 hours. Then we found out, like, after a day, we saw the fragmentation problem. And that's where we discovered that, like, we had lots of different regions which were all like 85% alive, 15% dead, and like we had all this garbage that would never get cleaned up, because over time, the fragmentation would distribute itself relatively evenly throughout the tenured space. And so we controlled for that by raising the liveness percent for inclusion in the C-set from the default of 65% to 90%, and that's how we solve these problems. Each one of those slides with the like special tuning is a week of my life in pain, distilled for you.
That's what I wanted to know. Thanks.
Hi. Hi. When we tried with G1, we faced some problems due to the humongous allocations. How it impacted you? Any impacts?
Which allocations?
Humongous allocations.
Humongous objects. Yeah, so the way I would, we didn't have that problem, but in part, humongous object allocations are a good indication that you shouldn't be evaluating fixing this problem by tuning your collector, but you should be going and profiling your code and figuring out where those humongous objects are coming from, and if you can break them up. Performance tuning doesn't solve architectural choices that may make something like G1 unworkable. Most of our objects are relatively small, but it's entirely possible that G1 isn't workable, or that you need to increase your region size, or you need to do something like use transparent huge pages. This talk is only 30 minutes or so, 25 minutes, so there's the like cache hits on the processor, the benefit of like huge pages versus not huge pages. Like we all investigated all of these, and like that didn't make the cut for these slides. At the end of the day, though, like you're going to need to go and decide, like, do we need these humongous objects allocated, or can we break these objects up into several different objects? Because most of the time, those kinds of issues usually indicate an issue with the software rather than with the collector itself.
Okay. It wasn't proper usage. With CMS collector active, it just took, plus parallel plus CMS collector active, it just took 5 minor cycles to collect those objects. But with G1, it went till OAMs.
Yeah, and as with everything, tuning something to work effectively for your service can't be universalized. If it could easily be done, this talk would be much less interesting, because it would be, I turned on G1 and it just worked.
Okay. Okay, it would be better if we have humongous tuned some more for a threshold. If there is a 50% allocated as humongous, they may reclaim that. Okay, fine. Thank you.
All right, thank you, everyone.